Today, overhead extra high voltage transmission lines can operate at up to 1.1 million volts. But in underground transmission, engineering challenges can begin at voltages as low as 11,000 volts. Even then, Japan has already transmitted 500 kV class power through underground cables. Look at this visual. On one side, an overhead transmission line enters the switchyard, which on the other side, the same power route enters through a high voltage cable. In an overhead line, the surrounding air acts as the main insulator, so the line can reach the gantry tower directly and terminate there. From here, power flows into the switchyard and is distributed through different feeders. Two devices are important here. The first is the lightning arrestor, which diverts overvoltage surges safely to Earth and protects the system from lightning. After that comes the CVT, which steps down and measures the high voltage for protection and metering. Now let's see what happens when the same line enters through a cable. Inside the cable, the conductor is insulated within a sealed structure. But as soon as it reaches the switchyard, the conductor enters the open environment. At this point, the insulation medium changes, and this creates the main challenge in cable termination. When the cable conductor is cut, the electric field starts concentrating strongly around its sharp edges. If this field is not controlled, the cable insulation can be damaged. This may allow the conductor to come into contact with Earth, causing a major fault. To understand this, we need to look at the cable design. At the center of the cable is the main conductor, made from many small thin strands. These strands do not just make the cable flexible, they're also important because of how current behaves. If the conductor were made as a solid rod, most of the current would flow near its outer surface. As frequency increases, the current moves even closer to the surface, leaving much of the inner area unused. This is called the skin effect, and it is one reason conductors are made from many small strands. To reduce the skin effect more effectively, different conductor designs are used in high voltage cables. In this visual, you can see two examples. The first is a round stranded conductor, and the second is a Millikan conductor. These conductors can be made from either aluminum or copper. When high voltage is applied to this conductor, an electric field forms around it. Ideally, this field should be uniform, but even a small manufacturing defect on the surface of a strand can concentrate the field at this point, which may later damage the insulation. To make this field uniform, a conductor screen is applied around the conductor. This semiconductor layer makes the conductor surface electrically smooth and helps distribute the electric field evenly. One important point must be understood here. The safe voltage limit is not decided by the conductor alone. It is mainly decided by the insulation system around it. In an overhead line, as the voltage increases, the conductor is placed higher above the ground. This allows air to act as proper insulation between the conductor and the earth. Similarly, inside the cable, xlpe insulation is applied over the conductor screen. In a 400 kV cable, this insulation can be around 26 millimeters thick. If the conductor screen is removed, the electric field becomes non-uniform again. During long-term operation, this concentrated electrical stress can damage the insulation and increase the risk of a fault inside the cable. But the first electric field does not stop suddenly at the xlpe insulation, so it must be terminated properly. For this, an insulation screen is applied, helping the electric field end in a controlled and smooth way. A metallic screen is applied around the insulation screen. Any voltage induced by the electric field is given a safe path to Earth through this metallic screen. It is also called a metallic sheath, and depending on the cable design, an armor layer may also be added outside it. Finally, a PVC protective sheath is applied on the outermost layer. It protects the cable from external physical damage and moisture. When the cable reaches the substation, the metallic screen is properly earthed. If induced voltage or any faulty condition occurs inside the cable, this screen safely carries the unwanted current to Earth. When high voltage transmission takes place through these cables, major engineering challenges appear. To understand this, look at an extra high voltage overhead line, such as a 765 kV line. Its humming noise can be heard even from the ground. In reality, the conductor of a transmission line creates an electric field around it. The conductor is surrounded by air, which we normally consider an insulator. But under a high-voltage electric field, air particles begin to ionize, producing the humming. Even from about 1 foot away from the conductor, this electric field can still cause a strong electric shock. As the distance from the conductor towards the ground increases, the field becomes weaker, but some electrical effect can still reach the ground. If we look at this carefully, the air between the transmission line and the ground becomes charged because of the electric field. In this condition, the line conductor behaves like a positive plate, while the ground behaves like a negative plate. This creates an effect similar to a charged capacitor. This capacitive interference can increase the voltage at the receiving end, meaning the received voltage may become higher than the voltage originally sent. Now look at the cable. Here, xlpe insulation sits between the conductor and the metallic screen, just as air acts as insulation in an overhead line. But inside the cable, this gap is very small. As a result, a capacitor-like effect forms between the conductor and the metallic screen, and capacitive interference appears again. If we compare an overhead line with a cable, capacitive interference is higher in the cable. In an overhead line, there is a much greater distance between the conductor and the ground, but in a cable, only a few millimeters separate the conductor from the metallic screen. As a result, the receiving end voltage can rise significantly. If the cable is operating under no load condition, this capacitive interference can become even stronger. But cable insulation is designed for a specific voltage range, so when the voltage rises beyond that limit, the risk of insulation damage and faults also increases. In extra high voltage overhead lines, capacitive interference becomes noticeable over long distances. To control it, a shunt reactor is collected in parallel with the line, usually inside the switchyard. But in a cable, this effect can become significant, even over 30 to 40 kilometers. So a cable system may need a shunt reactor much earlier. So far, this was about transmission. But terminating the cable inside the switchyard is also a major engineering challenge. Because of the intense electric field at the cable's sharp edges, the insulation can be damaged. This is why a silicone rubber stress cone is fitted over the xlpe insulation. But it must sit perfectly on the insulation, because even a tiny air gap or dust particle between them can disturb the electric field. Now look at the field lines. The field is strongest at the point where the cone touches the insulation. As we move further away, the field gradually reduces. This creates a smooth voltage gradient and helps control the electric field. Here, the metallic sheath is properly earthed. After this, the conductor screen is removed, and the main conductor is connected to the connector. Finally, the external insulator housing is fitted over the stress cone and conductor assembly. A corona ring is installed around the insulator. At the terminal end, the electric field can concentrate around the edges. As a result, small sparks may be visible at night, known as corona discharge. The corona ring controls this discharge by redistributing the electric field. From here, the line connects to the switchyard equipment. In an overhead transmission line, the lightning arresters diverts lightning surges safely to Earth. In cable transmission, there is no direct lightning strike on the cable, but the LA is still used to earth any surges that enter the system. The equipment ahead mostly remains the same. Routing cables in underground transmission is also a major challenge. In many places, large trenches are made, but the cable cannot be bent sharply, as this can create stress in the insulation. That is why the route is designed according to the cable's proper bending radius. In many places, cables are also laid inside ducts or pipe housing for protection and proper routing. In three-phase transmission, each phase usually has a separate cable conductor, known as a single-core cable. But up to 11,000 volts, a three-core cable can also be used. If high voltage needs to be transmitted through cables over a very long distance, one alternative is DC transmission. It does not face the same capacitive interference problem, but it has its own engineering challenges. Both AC and DC cable transmission are costly, so the final choice depends on the requirement. If there is a large river between two cities, an ocean crossing is required, or the line has to pass through a sensitive or residential area, cable transmission is often used. We don't use AI-generated animation. Every visual is created originally by our small team. If you find our work valuable, please support us by subscribing to the channel and watch our other detailed engineering videos. Thank you.